As a follow-up of this exercise 1.1.7 on simplicial homology of tetrahedron, let's do one more exercise to compute the homology, singular homology of this projective plane RP2. We just want to say that homology group could have torsion phenomenon when this coefficient ring R is not filled. So let's take R to be the ring of integers z, and so recall that this RP2 could be represented by the following. Diagram. So we have two vertices with 1 with 2. But what we do is we still, although we want, so these are the same point, but still we fix an order on it. So which means the order we are fixing is firstly this, secondly this, thirdly this. And so the direction is, this is our order fixed. This is same as saying we have fixed an orientation. And then similarly we define what are C0, C1, C2. Correspondingly, there are 3 Z modules with bases. C0 with bases 2 vertices, V1, V2, C1 with bases 2 edges, E1, E2. So don't be confusing, though E1, E2 seems to both equal to V1, V2. If this is confusing, I think we could just do like this, and then this is just saying that fixed order at the beginning is, this is our fixed order at the beginning. And so this is our F1, for example. Okay, so correspondingly C2 has basis F1, F2, these two physics. Okay, let's now look at these differentials. Firstly, the D1. Again, this should be a 2 by 3 matrix, maps from D3 to D2. So the first column corresponding to record how the differential maps E1. The differential maps E1 to, because E1 is V1, V2. And so different maps E1 to V2 minus V1. So the first column corresponds to V2 minus V1. Correspondingly, E2 is mapped to, again, V1, V2, so again, V2 minus V1. E3 is mapped to V1 minus V1, so 0. Correspondingly, F1 is mapped to, so F1 is mapped to V1, V2, which is E1. Sorry, it should be. So by the orientation we just fixed, so F1 should be just V3 plus V2 minus V1. Sorry, E3 plus E2 minus E1. So this minus E1, for example, it corresponds to remove V1, tilt, and you got V1, V2. this partial f1, or say yes, partial f1 should be minus plus so E2 minus E1 plus E3. So correspondingly got this. Okay, so firstly compute H0, which is the kernel of D0, which is host Z0, Z2, 库什么 image of D1. So what is image of D1? Image of D1 is just the span of the column vector of this, which means it's just image of D1 is just span of minus 1, 1, which means just a span of V1 minus V2. While C0 in particular, you could find a basis V1 minus V2, so H0 is isomorphic to Z. Okay. For H1, you have to compute what is kernel of D1, the image of D2. Let's first look at D2. So D2 is the image of F1, the image of F2, as a linear combination with integer coefficient. Okay, which means image D2 is just E1 minus E1 plus E2 plus E3. Whatever integer coefficient plus whatever integer coefficients times E1 minus E2 plus E3. Let me copy here, and so image of D2 is just as what I said here. But you could also change a basis. Change a basis to be. So why do we do this? It's for later computation, but let me just mention this. You could change basis from this 2 to 2E3, which means you add them together and you keep the second one. Okay, in particular, you say that the kernel of D2 is 0. This tells you that H2 is isomorphic to 0. So what is left to compute is H1. So now we have image of D2, which is contained in kernel of D1. Kernel of D1 you could solve this homogeneous linear system, or you just notice it's not difficult. You could solve this. Which means consists of all the vectors with bases I'm talking about kernel D1 with bases AJs E1, E2, E3, whose coordinates satisfied x1 plus x2 equals 0. So x1 equals minus x2. x2 is free variable, could be whatever it is, and x3 is also free variable, could be whatever it is. And so this is the integral span of -1, 1, 0 and 0, 0, 1, which corresponds to C3 and E1 minus C2. Sorry. Now because of this coefficients are not filled, you cannot just talking about the dimension. You cannot just count the number of bases, the number of vectors in bases. You have to look precisely into their inclusion relation. So this kernel of D1, by changing a basis, you could write it as J, the integer span of E3, and integer span of E1 minus E2 plus E3, and so basically you compare this inclusion into this, and so obviously the quotient should be the E3 quotient by 2Z3, and so isomorphic to the quotient by 2. This is an example of simplicial homology which has torsion.